You call it a buoy, don't you, when it floats in the water?
Yeah, I mean, I started sailing on British ships, so it sounds weird either way I say it now, because I started by calling it a buoy.
Yes, that's the way you put it.
But they both sound weird now.
How come you got to hear buoy? Because I believe that's a British term, unless you were on the East Coast.
Yeah, that was the ships I sailed on to start with were British, and I'm Canadian. We say boy as well up there.
God, you got a complicated career. So you're a Canadian living in America, right? And I'm a Scottish person living in America, so we share quite a few things. Well, good morning, everyone. Let's get started. My goal today is to get finished our section on calculating surface areas, right? So I've basically trying to write down all 4 equations and when you should use them, because in the later questions, it gets a little bit less obvious which equation, which equation belongs with which question. So first thing you need to look for is which axes it's being rotated in. So if you are told that it's being rotated in the x-axis, then it has to be one of these 2 equations. If you're being told that the curve is being rotated in the y-axis, it needs to be one of these 2. So you read the question, and typically at the end, it'll say rotated in the x-axis. So that means forget about them, it's one of these 2. And then you look at what other information they're given. If the question then tells you everything in terms of x's, so they say y equals x cubed plus x, and x is between 4 and 7, whatever, then you're going to use this one. If they tell you the equation and they say it like x equals y cubed plus y, and it goes from y equals 4 to 7, then you use this one. And once you have identified the correct equation, you then just follow the process. Now, if on the other hand, it's rotated about the y-axis, which is the ones we're going to spend more time on today, it's one of these 2. Now, if the information is given in terms of x, right? So this is the curve and x is from 1 to 2. This is the formula that you use. And if it's rotated about the y-axis, but the information is in terms of y, like x equals y cubed plus y, and y is between 3 and 4, very often it's easier to look at this piece of information because it's clearer. Y between 1 and 2 and y x between 1 and 2. That's pretty clear. Sometimes it's not so clear in the equation because in the later questions, they aren't written quite like that. They'll be written as x squared plus y squared equals 9, right? In which case you don't really know, is it an x or is it a y? But if you look later, you'll find out from here what's going on. So that's kind of where we are right now. So let's jump right into our first equation, which I don't think I've done. If I have, tell me and I'll do a different one. And this is going to be like question 13. And it's a rather weird looking function. Okay. So we have 4 equations. Here they are. I'm calling them 1, 2, 3, and 4, so it's easy to tell me which one. This shape is being rotated. About, let's double check, about the y-axis. So here's an equation. Here's the y going from 0 to 8, and you're being told it's rotated about the y-axis. Which one of these 4 is the one that you use in that story?
I wouldn't use the 4th one.
And the reason you chose that, I'm assuming, is because it's rotated or reflected, right?
Yeah.
Right. And this one, not so obvious that it's x's or y's here, but would you agree that is obviously y? So the clue was here. So that means that we are going to find the surface area by finding the integral from c to d 2 pi g of y, the square root of 1 plus g of y squared dy. Now, this guy doesn't quite work with this, and that's because this is not written as x as a function of y. So what I'm going to do is I'm going to subtract y to the power of 2/3 from both sides. And then I'm going to isolate the x. Okay, a little bit weird. If this was x squared, wouldn't you take the square root? And if it was x to the third, wouldn't you cube it? But it's x to the 2/3. So what power goes here? What power goes up here?
3/2.
Correct. Essentially the reciprocal. Right. Now that guy is essentially your g of y. So I'm now going to find his derivative. So I'm going to multiply by the power and reduce the power by 1 to get a half. And then I'm going to differentiate with this ugly looking guy. Excuse me. Oh, stupid bloody flu or cold, whatever I've got, it's a pain in the butt. So you get negative 2/3 y to the negative 1/3. Are we good on that? Any problems? Are we comfortable? Right, now that's one ugly looking expression, and I didn't leave enough room here, so I'm going to do it over here. G dashed of y is negative 4 take away y to the 2/3 raised to the power of half times y to the negative 1/3. That's where we are right now. So I'm going to take this guy and square it and add 1. And so it's going to be 1 plus all of this stuff. Something like that, squared. Right, you can square that, makes it positive. You square a half power, you get that. And if you square this guy, you get that. So far, so good. Any questions? Feeling good? Right, what do you think I'm going to do next to this expression? Right, it's pure algebra. How am I going to rewrite this in such a way that I can make it look prettier? Because right now it's not really that pretty.
Distribute the y to the negative 2/3.
What do you want me to? It could be right. I just didn't catch the beginning, Mia. What did you want me to do?
Distribute that y.
Okay, so if you distribute it, you get that. And you know, if you multiply this guy by that guy, don't you get negative y to the 0? Isn't that a really amazing result? So we can now plug it into here. So it's going to be the integral from 0 to 8, 2 pi, this function, times the derivative guy, which is this fellow. And it's going to be 4y to the negative 2/3 dy. That's going to be 2 pi, pull that out. Just going to leave that ugly mess kind of on its own. If you find the square root of this, you get a 2, and the square root of that guy is negative 1/3. So we're now looking at 4 pi, the integral from 0 to 8, 4 take away y to the 2/3 raised to the power of 3/2 times a y to the negative 1/3 dy. That is one ugly looking integral, but it's actually not that difficult to do. It's actually a u sub. What u sub should I use for this question?
Four minus 2 or 3.
Yeah. And I'm assuming that you chose that because it's the ugly guy inside this bracket, which is a good candidate. Now, when you differentiate with respect to y, you get negative 2/3 y to the negative 1/3. Okay. Now, if you do the crossover, you get negative 2/3 y to negative 1/3 dy. And if you divide both sides by that ugly guy, it does get a bit messy. And no matter how I do it, it's just going to look messy. So why don't I just pretend that it's that guy and not actually make any attempt to make it look pretty? So over here, it's 4 pi, the integral of u to the power of 3/2 times that fella times this weird, ugly looking fella, du. And then these two cancel. Would you agree that 1 over negative 2/3 is just another way of saying negative 3/2? Right? 1 over negative 2/3 is just another version of negative 3/2. So I'll suck the negative 3/2 out and I will get a negative 6 pi. The integral of u to 3/2 du. Power rule. Add 1 to power, divide by the new power. Convert that guy into 4 take away y to 2/3. Technically, it's being raised to the power of 5/2. And take that entire mess and replace it from y equals 0 to y equals 8. And yes, it's very ugly, but it's also correct. So can I just let you play about with plugging the numbers in? They're not as bad as you think. For instance, do you know that y 8 to the power of 2/3 is actually 4? And 4 take away 4 is 0. Do you see how that came out quite nice? Now, when you plug in 0, 4 to the power of 5/2 is 32, and that actually comes out quite nice. And it'll be a negative, and that negative cancels out that one. So it's actually not as bad as I kind of told you it was going to be. But would you agree that there is an awful lot of algebra and places you could easily slip up? But it is doable. I'm going to do some more of these guys, but I think before I do that, we have got 4 different possible integrals to do. So I'm just going to pick some questions and tell you what the question is, and then we'll decide, is it 1, 2, 3, or 4, okay? So this is question 14, and the curve that we're going to rotate is a squared take away y squared, and it's going to be from y equals 0 to a over 5, and this is going to be reflected in the y-axis. Okay, number 1, 2, 3, or 4. Which equation will we use in question 14? 1, 2, 1, 2, 3, or 4? I see a 4. Would you agree? It's rotated in the Y, so it has to be one of these two. Isn't it the one with all the Y's in it, which is number 4? So you are going to be using the integral from C to D 2 pi g of y square root of 1 plus g dashed of y whole squared dy. And from now on, I'm just going to tell you the number. Okay, now let's look at the next one then. The next one, question 15, says xy equals 2y squared minus 1. And it's 1 y between 1 and 4. But this is being reflected. I'm saying reflected, I should really say rotated. This is being rotated in the x-axis. One, two, three, or 4. Which one will it be for this one? I see 2. So you're agreeing it's in one of these two? And would it be the one with all the y's in it? Right? Now, when you look at this equation, do you see it's not quite right? But isn't that the clue? It's kind of hard to disguise that. It is quite hard to disguise that. So wouldn't you have to rearrange this guy by dividing everybody by y? And after a little work, it's not that bad. Would you agree? That's doable, right? It's not the ugliest looking thing in the world. And that was number 2. Let's see what 16 has. We have x equals y plus 2y cubed. The y is going to be from 0 to 1. And it's going to be rotated in the y-axis. So 1, 2, 3, or 4 this time. Right. We're getting faster at this. Is it easier once you've seen a few, one after the other, just to get used to it? And because once you know the formula, isn't the process just do whatever the formula tells you you need to do, right? And then you've got all the hassling, you know, making it look pretty. And that's not easy, but at least you know what you have to do. And this is 17. X is 2 cos squared y, and it's 0 to y to pi upon 2, and it's going to be about the y-axis again. Well, y-axis in this last grip. What are you going to do this time? I see a 4 again. I mean, although these are different questions, aren't they essentially the same kind of information? So it should be the same formula. Okay, any others left? Okay, how about 18? We have y equals 1 over x, and it's from 1 to 3. And we're going to do it about the x-axis. Okay. I see a 1. You agree? Number 1. We're almost finished this bit. 19. Y equals that guy. X between 0 and 2. And we're being told to rotate this shape about the x-axis. Which one does that job? It's back to being 1 again. Can we pretend that it was the same information, but they wanted to rotate it about the y-axis? Which one would you use if you wanted to rotate that curve about the y-axis? Which number? I see 3. Do you agree it's this one over here? Do you see why all 3 pieces of information are important, aren't they? Knowing which axis it's being rotated in, doesn't it have an effect on which formula that you use? Knowing what the information looks like, is it in x's or is it in y's? Doesn't that also decide which of these two or which of these two you're going to use? Okay, so do we feel comfortable if I gave you a curve that you would know which formula to do? You feel comfortable with that? Right. So let me rewind and show you some questions. Here are 6 questions that we've kind of covered. since we can't cover all of them because we just don't have time, let's cover 2 of them. So out of those 6 ones, which 2 would you like to see? Which 2 look ugly or you're not sure how you would tackle them? Just give me one right now and we'll pick the other one after this.
Yeah, what about 17?
Let's do 17.
I was just about to say the same thing. Yeah.
Yeah. Well, you know, the minute you see trig, don't you kind of go, oh dear, right? Because trig has its own extra difficulties, doesn't it? Because it has trig identities to deal with. So let's see what this one is. It's going to be x is 2 cos squared y. The y is going to be from 0 to 1. That's a bit interesting. Let me check that. I've 17. I'm scanning wrong. There, that's better. I was wondering why that wasn't a version of pi, which it is. And it's going to be about the y-axis. And we've already decided that it's going to be this formula. So I'm just going to write down the basics of it. It's going to be from 0 to pi upon 2 pi g of y, followed by 1 plus g dashed of y squared dy. And I'm just checking what the answer is going to be when I'm finished. Ah, okay. Not what I was expecting. So I'll start off with the 2 cos squared y guy, and I will differentiate him. And I hope you recognize a chain rule. So it's basically cos x, you know, if you want to, it's really that guy, right? So when you do the chain rule, you multiply by the power, you reduce the power by 1, and then you differentiate by this guy, and the derivative of this guy, that's our dog telling us there's a leaf falling somewhere. So -4 sine y cosine y. That's okay, not free. So 1 plus its derivative squared is going to be 1 plus -4 sine y cosine y squared. Well, that gets us 1 plus 16 sine squared y cos squared y. So I'm looking at that, and to be honest, there isn't any trig identity that comes to mind. So I'm going to assume, as I think I'm correct in assuming, there's nothing I can do to that, right? Sometimes, well, lots of the times, isn't there an identity and it turns into something nice? Can we pretend for a minute that it was 1 plus tan squared, for instance? Wouldn't that become secant squared, right? Or might it be 4 sine squared plus 4 cos squared plus 1, you know, something like that? Well, if that happened, wouldn't the 4 sine squared plus the 4 cos squared just give you 4, and 4 plus 1 gets you 5, right? So in this case, nothing nice is happening, so that's fine. And so we have the integral from 0 to pi upon 2 pi, this guy, 2 cosine squared y, times the square root of this guy. I'm going to tidy it up just a little bit. And we're looking at that guy. So when we picked that one, I looked at the answer, and you know, it's a way to keep track I'm going the right place. Normally, you would expect this to keep going. And normally that's true because you're expected to find the exact value. But in this question, they want a decimal approximation, which makes things actually quite easy. You have to put that into your calculator and find the area under that curve. Now, I don't know. I don't know if you've actually ever used your TI-84 to find numerical estimates for areas under curves. Now, hopefully you have, but if you haven't, this is what you would do. First, you'd make sure that you're in radians, which I'm glad I checked because I wasn't. Then you type y equals, and you type in all of this stuff. So 4 pi. Now, to get things that are squared, you have to be a little bit awkward. You have to do bracket, cosine. I know I can't have y's, but I'll use x to replace the y. So that's how you do 4 cos squared, right? It's a bit clunky, but that's how you do it. Then you go multiplied by the square root, 1 plus 16 times. Now, sine squared, cos squared, well, I could do it just the way it's written. So do a bracket, sine squared times do a bracket, cos. Hopefully I put all the right number of brackets here. Squared. And I think I might need another bracket for the square root. Let's find out. And I'm just going to go to window and do 0 to pi upon 2. And I'll just do a zoom to fit, and that'll tell me if I've typed it in right. And I didn't. Okay, so let's find out where my brackets are missing. 4 cosine x's, that's good, squared. What's that? Looks like a funny bracket. Times. I wonder if that's what it was. Square root of 1 plus that guy squared times that guy squared. That looks much better. Let's do another zoom to fit. Shouldn't take that long. Go down. There you go. Some boring curve. The boring curve by actually is this guy. I guess it's taking so long because it's such a big curve. And now that's just to check. Second calc, option 7. Lower limit 0. Press enter. Upper limit pi divided by 2. Hit enter. Does a little fill-in thing. And at the end, it better say 16.557, or I've screwed up. And it does, 16.557, and that's what they're looking for. So far, so good. Now, you can actually use this numerical estimate to check the exact value ones, right? So if you do a really ugly one and the answer ends up being, 4 pi plus the square root of 7, can't you do it this way and then find out what 4 pi plus the square root of 7 is as a decimal? And if they both match, you've got the right answer. So that's the way you can check your answers. But it is quite, as you noticed, because one of my brackets was wrong, that you have to be careful. Okay, though, that was that one. Let's pick another one. Actually, we might even get 2. I thought we'd only have time for 2, but that one that we just did was a little bit quicker than I thought. Who do you want next? Mia, sorry, did you say a number?
14.
14 gets a job. Okay. Right, now 14 has some A's in it. That's a little bit different. I haven't seen that. So for question 14, X is going to be that fella. It's going to be this guy. And since it's been rotated about the y-axis, we're going to use our fourth formula. So we're going to be using the integral from C to D. That's essentially C and that's D. 2 pi g of y, the square root of 1 plus the derivative squared dy. Okay, so g of y is going to be rewritten as a fractional power. So that guy is going to be written as this. That's going to make it a little bit easier to differentiate. So I can multiply by the power, and then I reduce the power by 1. But I also have a chain rule going on here. So what do I finish off with? Chain rule. Times.
Would it just be 2a?
A squared is actually a number. So when you differentiate a squared, you actually get 0. This is the guy you differentiate.
Would it be negative 2y?
It would be, yes. And that fella becomes negative y, a squared take away y squared to the negative 1/2. I know we're in Calc 2, but have you noticed how much differentiation you do in Calc 2? It's not just all integration. Now, we're then going to take this fella and square him and add 1. So it's going to be 1 plus this expression squared. Square, square, square. Well, that becomes positive y squared. And if you square this guy, you get a squared minus y squared to negative 1. And now I'm going to return this fella into a fraction. We need style points. We need to make this thing as pretty as possible because that's the only way we're going to be able to take the square root of it. Any suggestions of how you add a 1 to this fraction?
The special version of 1, in this case, it'd be a squared minus y squared over a squared minus y squared.
Agreed. And something really nice, Arms. Would you agree that when you add the top together, you're just left with an a squared, and the bottom you're left with an a squared minus y squared? Would you agree that's much prettier than it was a second ago? And that's probably going to play well inside the square root. So let's find out what it looks like. It's going to be the integral from 0 to a over 5, 2 pi, the original function, the square root of a squared minus y squared, times the square root of this guy, which we just found a minute ago, and now I can't find it. Where are you hiding? It was a squared over the square root of a squared minus y squared dy. And I'm just going to focus on this guy. If you have the square root of a fraction, you can take the square root of the top and this, by the way, that guy's not got a square root in him, he's just that guy. And the square root of the bottom. And then you say, oh, that was nice. Cancel. So what you've got is just 2 pi a dy. A is just a constant. It's just a number like 2 and pi are numbers. So don't treat it any different. So when you integrate 2 pi a, you get 2 pi a y. Just like 5 gets you 5y, right? And 8 gets you 8y. 2 pi a gets you 2 pi a y. Evaluated at y equals 0 and y equals a over 5. So we get 2 pi a over 5, take away 0. And that gives me 2/5 pi a squared. Well, as far as answers go, that's actually quite a nice answer, right? It's quite a simple answer. I'll pick the last one. Let's do 18. This guy is just number 1. So the surface area is the integral from 1 to 3, 2 pi f of x times the square root of 1 plus the derivative of this guy squared. Okay, if I want to differentiate this guy, I think it would be helpful to write it as x in -1. And if they do that, can you trust me, its derivative eventually is -1 over x squared. So far, so good? Nah. This becomes 1 plus 1 over x to the 4. I'm trying desperately not to tell you by writing it down. This is not looking good, agreed? It is going to eventually work, but right now it doesn't look like it's going anywhere useful. But we got to, persevere. Would you agree it might be helpful to combine the 1 and the x to the 4? And me, I think you were the one that said what to do. Don't you just convert that to special version of 1? So we'll count that as a kind of, everybody should have seen that. What do you think I should do next then? Right, this is your homework question. What are you going to do next?
The square root of the top and then square root of the bottom.
Right? Can't do much with that, but can't I call the bottom x squared? And no, you're not allowed to call that x squared plus 1. You're not allowed to take the square root of 2 things added and separate them. You're allowed to take the square root of a fraction and separate them, but not the square root of an addition or a subtraction. The algebra doesn't work. So we are now looking at and I should have done this earlier, so let's do it right now. That's the guy. This is a real sneaky one. You get extra double, triple brownie points if you can tell me what the U sub is. And I'll tell you right now who it's not. It's not x cubed, it's not x to the 4, and it's not x to the 4 plus 1, which are all very good candidates for many other questions, but not this one.
Is it x squared?
Oh, Nathan, you get extra brownie points there. Was that an inspired guess, or do you get a feel for why that worked?
I kind of got a feel because I was thinking maybe we would put it into like maybe an x sub later on or something. Wasn't sure.
Sounds good. I like your thinking because it's a good way to look at it. So differentiate, crossover, isolate the dx. So what do we have? 2 pi, an integral of the square root of u squared plus 1, because won't x to the 4 just be x squared squared? Now we have on the bottom an x cubed, and then we're going to have a 1 over 2x du. And that 2 is going to cancel that, so you've got a pi. And right now I'm looking at u squared plus 1 over x to the 4 du. So far, so good. Agreed? How am I going to fix the x to the 4 in terms of u? What will x to the 4 be in terms of u?
U squared.
U squared. Now, I'm going to show you how you do that one. There are 2 ways to do that. Nathaniel was right. I think he was mentioning there's probably some kind of x sub, some trig sub going on, right? Technically, you could do that. Will you trust me? It'll take you about half an hour because it's really, really messy. Or you're allowed to do this now. I have got, if I can find the darn thing, in, here we go. Open this. That's a funny color. I've never seen that before. Let's kick out of here. If you, this is my other Calc 2 class, but they're identical in many ways. You notice there's a new guy called standard integral. Whenever you come to an integral, right, you've done everything and it's like the last bit of the puzzle, right? I've got this. This is as good as it's going to get. If you get an integral that's just not really feasible to do, you're going to hit this guy. Because basically somewhere else, somebody else got the answer for you. So we're looking for a square root of u squared plus 1 over a u squared. So I'm going to scroll down these and I'm looking for a square root of u squared plus 1 over u squared. Would you agree that 24 has that look? What is the value of a going to be then using 24? What number will a be in question 24? Because we want 1 squared plus u squared guy.
It will just be 1.
Just be 1. I'm writing this guy down, and then I'll switch over to my screen. You can see it. So it's negative a squared plus u squared over u plus the natural log of u plus the square root of a squared plus u squared, right? Okay, let's zoom back. These are called standard integrals. I'm pretty sure, didn't we do one where I told you what secant x was? Right, that's where you'd find it, in that same place. I think we might or might not, maybe in my lab class, I think we also did a secant cubed x, which you'd find there. And there's also the square root of 1 plus u squared, which you would find there. So this is that guy. Now, in our case, this fella has an e equals 1. So our fella is going to be 1 squared, which is 1 plus u squared over u, plus the natural log of u plus 1 squared, which is 1 u squared. Right. Oh. And now we can replace it by the x's. So it's 1 plus x squared. Oh no, x squared squared, so x to the 4 over x squared, that's better. Plus the natural log of x squared plus the square root of 1 plus x squared squared, which is x to the 4. And that's the guy that we will evaluate at 1 and at 3. And God, that's an ugly answer, but it is the answer. Can you imagine plugging 3s in here and getting a number and 3s in here? And it's going to be, yeah, it's going to be ugly as heck, but it is the correct answer. So when you do integrals and you get to a place where you know that's as good as you're ever going to get, right? You might want to look up the table of integrals in Canvas now and go hunting for the guy that looks like him. Okay, last name and bye-bye.
I had a question.
Sure.
Did the pi just go away, or is
No, it didn't.
or what happened?
It's still there.
Okay.
I just forgot it. That is one cool question. If I told you 9 weeks ago that you were going to do this question, you probably would have run out the room screaming, right? But it's not as scary once you see things or you get used to things. It's not as scary. Okay, anybody get any more questions? It's bye-bye now. Bye-bye.